The next transformation that we're going to attempt to graph are horizontal transformations. These transformations are going to be stretch or shrink, so we either compress them or stretch them away from the y-axis. They give you a few looks of these. If you multiply by 2, you can see that the red line gets more rapid. If you go by half, you can see that it gets stretched out a little bit horizontally. To go back and put some context on what we've done already, we've had a function that said y equals f at x. If we put in f of b times x, anything inside parentheses was going to be a horizontal transformation. If we multiply, it's a horizontal stretch and shrink. So this represents a horizontal stretch slash shrink, which is either going to compress it or expand it away from the y-axis. Some of our basic rules that anytime it's happening to the input value first before we take the trig value on it, it's going to be counterintuitive. So inside the parentheses, it was more or less our counterintuitive idea, which means when b was greater than 1, we think about multiplying by numbers bigger than 1, like 2 and 3. We think of it stretching, but this actually is going to shrink your graph, so it's going to compress it towards the y-axis. So it's going to compress. When b had a value between 0 and 1, then it was a stretch. This is where we elongated the graph, so it's going to expand the graph horizontally. So there's some basic concepts that we had to learn, and we want to apply them just to a new function. Remember, anytime it's inside grouping symbols, it's a horizontal. If it's multiplication, it's a stretch or shrink. You get this counterintuitive idea. When it's bigger than 1, it's going to shrink the graph. If the value of b is less than 1, it's going to stretch the graph. It's going to expand it wider or away from the y-axis. They have some summaries of this. One of the things I'd like to highlight in here, they have a way of calculating the period of your graph. If you want to know what your period of your graph is going to be, you take your normal period for sine and cosine, you divide it by b, and b is what is going to control the length of that period. It's going to be the stretch or the shrink of that horizontal axis. So that's part of the preliminary ideas that we have here. Okay, so the next thing we're going to do is I'm going to try to bring back, hopefully you have a connection back to your core mathematics, because I want to think about this in more of an intuitive way, and then we'll come back to the formula way. And that was, we had, in the core math books, we thought of this as being a Ferris wheel. And in this Ferris wheel, we could make it whatever radius we wanted, and that radius was the amplitude. And then we looked at the amplitude changes of the previous one. I never introduced the idea because it really is pretty simple to do just by your vertical stretch and shrink. But the amplitude represented the radius of the circle. So we're going to keep the radius of the circle 1 here for the time being. But what we're going to do is we're going to change the speed at which we rotate around the Ferris wheel. Backtracking just a little bit further, and that is the value of the radian units of measure. This is where the radians become much more versatile. Radians were a unitless measurement, so that means what we can do is we can represent anything that we want as far as we rotate around here. This angle theta can be whatever units we want it to be. So a lot of times when we're dealing with this, we're going to let theta be equal to a unit of time, which means we can put in any real number that we choose to put in for theta because it is unitless, and then we can apply the units as we feel fit or as they apply in our example. So in this example, I'm coming back to what we did in the core book earlier. They said if this is a Ferris wheel and we have y equals the cosine of x, this really has a 1 in front of it, so b is a 1. So when b is a 1, we have an equivalency. It takes it 2 pi radians to go around the outside edge. Now radians can be whatever unit we want, so we're going to say it takes 2 pi units of time, and I'll say minutes to complete 1 rotation around this Ferris wheel, which would be really slow for a Ferris wheel. That's about 6.28 minutes. So whatever label you want. Maybe we'll have a little bit more fun if we go 6.28 seconds, then we'll have to hold on to our hats. But whenever we have, whether it's sine or cosine, if there's a 1 in front of that, what we're thinking of is the parent functions have a normal period of 2 pi, so to complete the ride it takes 6.28 seconds approximately or exactly 2 pi seconds, or whatever you want to use for a unit of time to finish your ride. Now let's come over to g of x. G of x has an equation that says it's the cosine of, I'm going to rewrite it as 1/2 times x. Now this value of 1/2 is the value of b. Now if I think of this in a Ferris wheel, this was like a gear being in gear 1, and this was in gear 1. When we were in gear 1, it took us 6.28, about 2 pi units to go around the circle. Now this is to make it even slower. We're going to put it in gear, you can think of it as that, half a gear, which means we're going to slow the Ferris wheel ride by half the speed of what it used to go. So we're still going to go around the Ferris wheel one time, but it's going to take, we're going to go at a speed of half as fast, which is going to take our time, and it's going to double it. So when b was equal to 1, we had a period of 2 pi. But when b is equal to 1/2, we're slowing down the rotation of the Ferris wheel by a factor of 2, which means we have to increase the period, or the amount of time it takes to go around the circle, by double. So it's 4 pi. So what we're going to have is a period of 4 pi for this in a particular graph. Now if you strictly use their formula, which is simple to use, they say that the period has got to be equal to the calculation of 2 pi divided by the absolute value of b. Well, in our problem, our value of b is 1/2. So it's 2 pi divided by 1/2, but dividing by 1/2 is multiplying by the reciprocal. So again, we get 4 pi for our period. So we've established the fact that the period of this thing is equal to 4 pi. Okay, so now the trick is going to be, how do we graph both of these on the same axes? And that takes a little bit of effort in thinking ahead of time before you just dive right in and start labeling your axes. So what I want to make sure that I do is I want to be able to graph one full period of the cosine of pi halves, but I also want to make sure that it's convenient to graph the original function, which is the cosine of x. So what I want to do then is make sure that I get the period of 4 pi on here, and how could I label this in a reasonable manner. So what I'm going to do is I'm going to go by pi halves, since we're going to, that's kind of our benchmark. So we're going to go pi halves, pi, and then 3 pi halves, and then 2 pi. Now that should capture the parent function. And now we're going to go to capturing our adjusted function, which is going to be 2 pi. Another pi would be 5 pi halves. Another pi under that would be 6 pi halves, or 3 pi. And another pi under that. So we're going up by a half pi every time. So 1/2, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves. This is 7 halves pi. And then by the time we get out to 8 pi halves, that's 4 pi. Okay, so sketching our first curve, the cosine of x. Now our parent function cosine of x, if we think about our unit circle over here, we want to go to a positive one, we're going to go to a negative one, and the cosine of 0 is 1. The cosine of pi halves is 0. The cosine of pi is a negative 1. 3 pi halves is 0. 2 pi is a 1, and it's going to repeat those values again. And by 4 pi, we're back to the top. So here we are riding the Ferris wheel. This is a nice leisurely little ride on the Ferris wheel. It takes us about 6.28 seconds to complete one rotation. Now on the other one, what we've got is a graph of 4 pi. Okay, so we got to start and finish at the same place after 4 pi units. So here's how I would graph these. We're going to start at the same location as we did with our other graph, but it's going to take us twice as long. It's going to take us till 4 pi till we get back to the right. So that means we're going to go around this in 4 pi units. So half of that would be 2 pi units, and half of that would be pi units. So we're going by pi, 2 pi, 3 pi, 4 pi. We complete one rotation. So we start at time 0. Pi units later, we should be at its highest peak. So, I'm sorry, it should be at 0 because it's cosine. So at pi, we're at 0. The next stop that we have that's significant is halfway around, which is going to be 2 pi. And at 2 pi, the cosine value is going to be a negative 1. And then by the time we go 3/4 of the way around, we are 3 pi units into the ride, which means we're going to be back to 0 because our x value is 0. By the time we get to 4 pi, we're back to where we started. We're back to positive 1. So what you're seeing is the period length is being stretched or expanded. So where we used to have 2 periods, a red and a blue, we now only have 1. So multiplying by a factor of 1/2 stretched our graph to twice the width, and we only see 1 period versus the 2. So that's the first example of sketching and doing a horizontal stretch and shrink. Okay, the next example, to me, what we're looking at is a Ferris wheel ride where we have taken the gear and we have shifted into third gear, which is 3 times faster than our old one used to be. So when our original function was cosine of x, the sine of x is a gear of 1. We're going to triple that, which means we're going to speed up that ride. What used to take 2 pi units to go around, when b was equal to 1, period was 2 pi, we're going to put it in third gear. We're going to triple the speed, which should take the time and reduce it by 1/3. So our period should be 1/3 as long. So we're only going to have a period for our new one of 2 pi thirds. So our period for this is 2 pi thirds. And we can get by calculating their formula, the period is equal to 2 pi over b, but our value of b is 3, so there's our period of 2/3 pi. Now here's again where we're going to have to start thinking about how do we make sure that we get decent labels on the bottom of our x-axis so we can graph both of them on the same curve. So I know that by the time I get to a period of 2 pi thirds, I should have completed 1 rotation on this graph. So 1 rotation to me means I'm going to have 1, 2, 3, 4 tick marks on my graph. So by the time I get to these 4 tick marks, 1, 2, 3, 4, I need to be at 2 pi thirds because I've made 1 rotation around that graph on the speedy Ferris wheel. So I'm going to make sure I'm going by 2 pi thirds for 1 full rotation. But half of that would just be pi thirds. So if we complete this ride in 2 pi thirds, then halfway around should only take me pi thirds of a rotation. Then to get to a quarter of a turn should take me half of pi thirds, and half of pi thirds would be pi 6. So the units that I want to label this are pi 6. This is 1 pi 6, 2 pi 6, which reduces. Then we're going to have 3 pi 6, which is pi halves. Then we'll have 4 pi 6, and that's 2 pi thirds. Then 5 pi 6, 6 pi 6 is pi, 7 pi 6, 8 pi 6 is 4 pi thirds in lowest terms. Then we got 9 pi 6, which is 3 pi halves. Then we got 10 pi 6, which is 5 pi thirds. Then we got 11 pi 6. And then we finally have 12 pi 6, which is 2 pi. Now hopefully by the time I get done with this, you'll understand why I did that. The more difficult one to graph was the busy graph. This is where we really sped up the speed of that Ferris wheel, and we're zinging around there quite quickly. So we're doing a sine curve. Sine curves start at 0. Our sine of 0 is the y-coordinate 0. We want to finish this ride because our period is 2 pi thirds at the same location that we started. So we're going to rotate around this 1 time. We're going to be at the same spot we started at 0. Halfway around, or back here at pi thirds, we should be at 0 as well because we have a y-coordinate of 0. And the picture's getting really busy, but hopefully you can read through that. Then we take a quarter of a turn. By a quarter of a turn, we should be at pi 6, and pi 6 we should be at the highest point in our graph, which is 1 unit up. So then, every pi 6 we're going to have a quarter of a turn. At pi 6 we're at a positive 1. At pi 6, another pi 6 at pi thirds, we're going to be at 0. At pi halves, which is down here at a negative 1. And then by the time we get to 2 pi thirds, we complete 1 trip around this circle, or this Ferris wheel. So that's 1 period. Now we're going to do it again. We're going to repeat those values. A quarter of a turn, we should be at its highest point, so a quarter of a turn. Another quarter of a turn, we're at 0. Quarter of a turn, we're at negative 1. Quarter of a turn, we're at 0. We can do it again. Quarter of a turn, we're at positive 1. Quarter of a turn, 0. Another quarter of a turn, negative 1. Quarter of a turn, we're back to 0. So here's our curve with a period of 2 pi thirds. Now, in comparison, if we graph just the sine of x on a normal sine curve, when the value of b is 1, it takes us 2 pi to go around the whole thing. So a half a turn is pi, and a quarter of a turn is pi halves. So 1 pi halves, 2 pi halves, 3 pi halves, these are our values. So starting at 0 radians, we have a y value of 0, so we start at the same locations we had there. A quarter of a turn, or pi halves, we're finally at 1. Then we go a half a turn, we're at 0, so at pi, we're at 0. Then another quarter of a turn, at 3 pi halves, we're at a -1, so 3 pi halves is a -1. And by the time we do 2 pi, we're back to where we started. So here is our normal period of the sine. What we want to do is we want to triple that because we had to get 3 periods within 1, and you can see there's 1 period here, then the second period is here, and then the third period I'll leave in green. We have 3 complete revolutions when we triple the speed then versus our regular speed of 1. So there's our second one where we change the horizontal transformation. And then our final graph on this is cosine of x versus cosine of 1/4 x. So the 1/4 is taking our speed of our Ferris wheel and it has slowed it down. Normally when b is 1, the period is 2 pi. But if we take b and we slow the thing down by 1/4 the speed, that's 4 times slower, then our period has to grow and multiply by 4. So our period should be 8 pi. And again, if you apply their formula, the period is equal to 2 pi over b, and b in this case is 1/4. That means we have to take 2 pi and multiply times reciprocal, 4 over 1. And again, you're getting 8 pi. So either the intuitive analogy of the speed of the Ferris wheel, or you can go ahead and just apply the formula. But now we want to graph these. So again, to graph, we want to make sure we have reasonable tick marks on here, and I went ahead and did this a little bit ahead of time so that we can graph a little bit faster. On this one, our period is supposed to be 8 pi. So to go around the circle one time, it's going to take us 8 pi units. So a half a turn should take us 4 pi units, and a half of a half, or a quarter of a turn, should take 2 pi units. So we're going by 2 pi, 4 pi, 6 pi. So that's how I established the tick marks on my graph. So starting at 0, cosines get your x values. You're at the maximum height of 1. You go a quarter of a turn, and at 2 pi seconds later, you're at 0. You go another quarter of a turn, or halfway around the circle, which is here, you're at your lowest point, -1. At 6 pi, you're down at -0, -1, which is this ordered pair. We want the cosine value, which is 0. And by the time we go back to 8 pi, we should have completed 1 full rotation. Now, cosine curves start at the maximum, finish at a maximum. Its period is 4 pi, so 4 pi units later, I'm at the same spot. Halfway in between, we should be at our lowest point, and halfway in between there, we should be crossing the x-axis, and that's the way these things always will behave. So there's our cosine of 1/4 of x. Now let's go back and graph our cosine of our original function. The original function, we should be able to go around the circle at a little different speed. So typically, we go around the circle, and a parent function is 2 pi. So half of 2 pi is pi, and a quarter, half of pi, or a quarter of a turn, is pi halves. So we're going by 1 pi halves, 2 pi halves, 3 pi halves. So now we're riding the ride. We start at time 0. At time 0, the cosine curve is still 1. But now at a quarter of a turn, it takes us pi halves units of time. So pi halves is going to have to squeak that in there, because this is pi, and then this will be pi halves right in the middle of there. And then by the time we get down to pi, we got to be at a -1. So that's at our lowest point, -1. And by the time we get back to 3 pi halves, we got to be at 0. And by the time we get to 2 pi, we got to be back to where we started. So this thing really gets pinched inside of what I had in there for my units. But you can see that it finishes 1 period in 2 pi, where the other one only finishes 1 rotation in 8 pi. So I probably would have been better off not doing 2 rotations, but only 1 rotation. But that's our horizontal stretch and shrink. It takes a little practice to get better at those and good at stretching those things out. But you got the basic ideas intact now.